بلش. If you look in the night sky, you will probably see few tens, few hundreds, maybe few thousands of stars. And as you look long enough, let your eyes adjust to the darkness. Maybe you will have a sense of, you feel the silence, the mystery. And as the world around you fades, questions will start creeping in your thoughts. What are these objects? What are they made of? What's beyond them? Does it stretch forever in space? Does it last forever in time? Does it have a beginning? Does it have an end? In other words, is the universe infinite? Aristotle once argued that the universe cannot be infinite because in an infinite universe there is no special place. But there is a special place in our universe. You know where is this place? It's us. It's here. Everything seems to revolve around us. The sun rises from the east, it sets from the west. The stars follow the same pattern in the sky during the night and throughout the year. فينا نعمل شيء للصوت؟ تسمعوني؟ أحسن هيك؟ أحسن يمكن؟
فينا نجرب؟
تست
أحسن؟
تست I think أحسن ما في So Aristotle thought that the universe cannot be infinite because in an infinite universe there is no special place. And there is a special place in our universe, and this special place is us. We seem to be at the center of the universe, and everything seems to revolve around us. The sun rises every morning from the east, it sets in the west. The stars follow the same pattern during the night, the same path, and the same path throughout the year. And everything seems to be organized and permanent. For as long as humanity existed, we have built our civilizations under this illusion of permanence. Every empire has risen and fallen, but the stars remain unchanged. Yet today we know that the stars that we once thought eternal are not eternal. Stars are born, they live, and they die. Galaxies collide, evolve. Space itself is expanding. But the most haunting revelation of all of our human discovery is that if everything you can think of was meant to disappear, everything, me, you, the planet, the sun, the stars, the galaxies, the heat, the energy, the light, everything you could think of in the universe was meant to disappear, the universe will remain unchanged. Because 95% of its constituents are made of some mysterious form of matter called dark matter and the mysterious form of energy called dark energy. And these components shape the fate of the universe. Will the universe keep expanding to become colder and emptier, or is a more dramatic fate awaiting? In this talk, I will resume 14 billion years of cosmic history, and at the end, we will face the ultimate question: how will everything end? But before we do this, I want to take you on a tour across the universe. And we'll do this tour at the speed of light. Light is the fastest thing in the universe. It travels at 300,000 kilometers per second. It can go around Earth 7.5 times in 1 second. The distance to the moon is 1.5 seconds, light. Our sun is 8 minutes away. So a photon of light leaves the surface of the sun and it travels in space for 8 minutes to reach our eyes. So we look at the sun, we look 8 minutes in the past. This is our solar system. You all know it. It's 10 hours to the edge of Pluto. And this is the closest star to us in the universe. It's 4 light years away. So we look at this star, we look back in the past 4 years. It would take us 80,000 years to reach this star if we use the fastest object that we have ever built. It's the NASA's New Horizons spacecraft. This is a galaxy, so this is not a picture of our galaxy, but our galaxy looks something like this. It's a collection of stars. There are 110 to the power 12 stars, so one with 12 zeros. It's 100 billion stars and dust and gas. It's held by gravity and it rotates. So we are here now, 30 light years from the center, and it revolves. The galactic year takes 250 million years to make one full revolution. It will take us 2 billion years to cross the galaxy from one side to the other side. It's 100,000 light years. So light takes 100,000 years to cross the galaxy from one side to the other. All the stars you see in the night sky, even in the best night, are much less than this red dot that you see here. And we are revolving around the center of the galaxy at a speed of 220 kilometers per second. So me, you, this building, the planet, the sun, the solar system, the neighbor stars are going around the center of the galaxy at a speed of 220 kilometers per second. This is our neighbor galaxy, Andromeda. It's 220,000 light years, slightly bigger than us, and it's 2 million light years away. So the photons of light left this galaxy 2 million years back. We were not even Homo sapiens by then. We were not even, there were dinosaurs on Earth. So we look back, we look at this galaxy, we look back in time 2 million years. This is another one, M81, it's 11 million light years away. These are fantastic structures, all made of stars. Each one of them is the home of 100 billions of stars. They all rotate, they come in different shapes and different evolutionary patterns. So this is at 3 million light years. It turned out that the universe is filled with such things. Before 1922, we thought that our galaxy was the only universe, univers il, island universe. It turned out that the universe is made of these things. This is the Hubble Ultra Deep Field, so NASA decided to point the Hubble Space Telescope at the darkest patch of the sky. It collected light, the exposure is 11 days. For those of you who make photography, you open, تفتح الديافراغم تبع الكاميرا, 11 days collecting light. The size of this picture is 2.4 arc minutes. So you take the circle, is 360 degrees. You take 1 degree, you take 60 part of 1 degree, you take 2.4 from this, and this is the angle subtended on the sky of this picture. Okay? So we need 26 million pictures like this to cover the whole sky. There are a few thousands of galaxies in this. We are looking really back in time, 13 billion years back, right after the Big Bang. Every point in this picture, except these stars that are in the foreground, is a galaxy, and every galaxy is the home of 100 billions, few hundred billions of stars. So you do the math, you multiply this by the number of galaxies in each one, and by the number of stars in each galaxy, you get this number. It's 10 to the power 22. This is one with 22 zeros. If you cannot imagine how big is this number, think of the numbers of the grains of sand on all the beaches of the world. And there are more stars in the universe than there are grains of sand on all the beaches of the world. Our current vision of the universe dates from 1929. How do we know? I have to take you through some basics. Light, so for astronomy, light is very important. We cannot, it's not an experimental science, we cannot take 10 to the power 30 kilograms of gas, put it in the lab and wait 200 million years and then take a measurement. We only have the light that comes from us. Light is a wave, it behaves like a wave, and the wave is characterized by its wavelength. It's the distance between a crest and the crest, or a trough and the trough. And light comes in an infinity of different wavelengths. And every light you see is a mixture of all these waves on top of each other. The visible light that we see, this is the violet, it's 400 nanometers. So the distance between this and this is 400 nanometers. The nanometer is 1 millionth of a millimeter. So you take 1 millimeter, you divide by 1 million, you take 400 of these, you get violet. You take 700, you get red. Beyond the violet, shorter wavelengths, there is the ultraviolet, the X-rays, and the gamma rays. So ultraviolet اللي بتحطه protection على جسمكم على الشمس, it's light. It's not red, it's light, but you cannot see because our eyes only see this part of the spectrum. It turned out that we only see this part of the spectrum because we evolved as biological creatures next to a sun that emits most of its radiation in this part of the spectrum. If there was an alien civilization who stayed, I don't know, next to a star that emits in the X-ray, they maybe would have seen eyes that see in the X-rays. So when you go to the hospital, you get an X-ray. X-ray is light. It just goes through your tissue but doesn't go through your bones. And on the longer, there is the infrared. Infrared, we don't see the infrared with our eyes, but we emit infrared. يعني هلا أنا إذا بتعتموا ما بتشوفوني. إذا بتلبس goggle, infrared goggles, you will see me because I emit in the infrared. And then you have the microwave and the radio waves. Microwave is the microwave in your kitchen. It emits microwave light. It's light, but the wavelength is few millimeters. So this is light that interacts with the molecules of water in the food and it heats them. Okay? The second thing that you need to know, don't be afraid when you see the formula, don't freak out and leave the room. So this is a very important law. It tells that everybody that has a temperature emits light radiation. And the hotter the body, the shorter the wavelengths it emits. يعني هلا انا قلت لكم I'm radiating in the infrared, اذا بتحطوني بفرن تعلوا الحراره بصير احمر لونه بعدين بصير ابيض. Okay? So the higher temperature, the peak comes in the shorter wavelengths. And you know this law very well because you use it as architect every day in your life. When you select the color temperature of your lighting, when you specify your lighting design. So did you ever think why a color is associated to a temperature? This is the black body law. A black body with a 2000 degrees Kelvin will emit in the yellow, and the body is 8000 will emit in the blue. But we use it in opposite in architecture. We say hot and warm, but it's the opposite in reality. And this is a way for us to know the temperatures of the stars. So if you look at the night sky, you will see stars with different colors, and this is how we know the temperatures of the stars or any object we see in the universe. Astronomy started as a science when people started to take light and make it go through a prism. You all know this Pink Floyd album. So this is the white light, it goes through a prism and it diffracted. I told you about the waves of light on top of each other. This is a way to separate the waves of the light in their components. So this is basically a rainbow. This is a spectrum of the sun, our own sun. So it's the rainbow, the sun, but not in the sky, on a sophisticated CCD, on a very sophisticated camera. It's a very high resolution rainbow. You notice something strange. There are dark parts in the spectrum. There are parts of light that are missing. It took people time to realize this, but these are the fingerprints of chemical elements. It turned out that the light is emitted at the core of the sun, and when it travels through the gas, the atmosphere of the sun, which has hydrogen, helium, iron, silicon, sodium, they have these typical things. So they eat the light in this particular wavelengths. And every chemical element has a signature. So this is a hot source emitting light. The light goes through the gas. And what happens is that the gas eats part of the spectrum. So the light goes from the other side, missing some lines, but it spits it back in other directions. So you have an emission spectrum. When you look directly at the source of the light, you see the continuum. You see all the wavelengths. This is something you see every day in your life, but you never realize. When you look at the sun low at the horizon, the light of the sun goes through the gas, and parts of the light is scattered away. But it's scattered in all directions. When you look away from the sun, you see the sky is blue. So this is something similar in analogy to what happens in the stars, because here the light is not absorbed, it's just redirected. But in the star, it is absorbed and re-emitted. So this is a spectrum. When you see this with these four lines, it means there's a hydrogen atom. Hydrogen is the most abundant element in the universe. So Heidi Coop, this is a section through this. Okay? So when you see this dip, for example, corresponds to this one, and this dip corresponds to this one. So this is when you see this, you know that there is a hydrogen atom, and it emits. This is an emission spectrum. So when we look at the galaxy, we don't see individual stars. We see the light of 100 billions of stars together, because stars cannot be resolved. It's much smaller than a pixel on the CCD, we see this emission spectrum. And just to give you another background, so why this happens, because atoms, gas is made of atoms, atoms has nucleus and electrons occupy energy levels. So when an electron sees a photon of light with the same energy level, it jumps to another energy level and it absorbs the light and it jumps back and it spits it in this emission spectrum. Okay, this is just an additional information. In 1916, Vestus Leifer, an observational astronomer, looked at the spectra of galaxies. What he saw. So this is the hydrogen line, H alpha, that I showed you before. This is the spectrum of a galaxy. So this is the light from all the stars in the galaxies. It emits in the hydrogen because hydrogen is the most abundant element. And you notice something. This line should be here at 656 nanometers, but it's shifted rather. This is called redshift. So the light is redshifted to a longer wavelength. And there's a way to understand this. I'll take an example. If you stand by the road and close your eyes, you can immediately tell if a car is approaching you or going away from you. This is the Doppler effect. This is how the police radars give you speeding tickets. They know your velocity. Because of the frequency of the sound. You can listen here. When the car is approaching, the frequency is higher. When it's going away, the frequency of, not the amplitude of the sound, the frequency of the sound. غير النوت يعني. So this is the redshift, and we can quantify this, and this tells us about the velocity of the moving object. This is how the police radar knows how much you are speeding, and you cannot fool him because he can measure this exactly. Okay? So this is the spectrum of a receding galaxy, and it turned out that all the galaxies that were measured for the absorption, for the emission spectrum, all of them were redshifted. All of them had the emission moved away. It means that all of them were moving away from us. In every direction, Vestus Leifer looked, he watched the galaxies redshifted, and by different amounts, with different velocities. It's amazing. It seems that we are at the center, and everything is going away from us. And it took until 1929, 10 years later, until Hubble, Edwin Hubble, the most famous observational astronomers of all times. So what he did is he measured the velocities and the distance. And he noticed that for further galaxies, they move faster. And for shorter galaxies, closer galaxies to us, they move slower. For example, this is a galaxy. It is at 1 million parsecs, so a kiloparsec is 3,000 light years. It moves at 500 kilometers per second. If you go to 2 million parsecs, it's moving at 1,000 kilometers per second. And he had the guts to draw a line within this data. And he noticed that the further the galaxy is moving faster. And what is the equation of a line in the xy plane? Who remembers? Equation de droite x, y, y égale ax. A is a constant, so V equals hd, and h is the constant, and it tells us how fast the universe is expanding. It tells us the slope of this line. It's called the Hubble constant, and its measurement now is 70 kilometers per second per kiloparsec. So 1 kiloparsec away, the galaxies move 70 kilometers per second faster. You go 2 kiloparsecs, the galaxies move 140 kilometers faster. This challenged the Aristotelian belief. So the cosmos is not permanent, it changes, and we are not at the center of the universe. This is the most important intellectual revolution in our understanding of the world. Why we are not at the center? I just told you it looked like we are at the center and every galaxy is moving away from us. I'll tell you why. Imagine this is our universe, a two-dimensional universe, and these are the galaxies, and this universe, for some reason, expanded. It became bigger. So the distance between two galaxies became bigger. Imagine you are here. What you will see? You are here at the center. Every galaxy has moved away. The closest galaxy has moved a little bit. The furthest has moved much more in the same amount of time. So this is faster and this is slower. This is exactly what Hubble saw. But this happens when everywhere you are. So even if you are at this galaxy, you will think that you are at the center, and every galaxy has moved away from you. The furthest one have moved much more, and the closest one have moved much less. Even if you are here, even if you are here. So there is no center in an expanding universe. Every point in the universe is the center of the universe. In another thing people think about, if the universe is expanding, it's expanding into what? So people think it's a balloon that's growing inside a room, that's growing inside space. But this is a wrong analogy. This is a very big deal. It's very difficult to imagine this. So you have to think in 2 dimensions. Imagine you are an insect, and you are a very small insect living on the surface of a balloon. So for you, the world is 2-dimensional. So your world is not the balloon, it's the surface of the balloon. Okay? And imagine somebody come and blows this balloon away. You will see the other insects, you will see the distances getting bigger, right? But where the balloon is expanding, the insect is a 2-dimensional creature. For her, she doesn't realize that the 3rd dimension. احنا 3-dimensional, مانيش in 3-dimensional. أنا بمشي هيك وهيك هيك وبنط. هي بتمشي بس هيك وهيك. She cannot realize that it's expanding into another dimension. She just realized that the distances are getting bigger. So space, in an expanding universe, the universe is not expanding into space. Space itself is being created inside the universe. Space, even the space now is expanding, but very little, we cannot see it. In 1929, Hubble announced to the world that the universe is expanding. Now we'll go 300 years back. You all know this person, Newton. He was a curious young man. He was thinking about the world. Why things fall, why the apple falls and the moon does not fall. What is the nature of light? What is the nature of time? What is mass? What is acceleration? And he developed laws that we use every day in our life. Every day we use them. The satellite motions, ما في كان GPS على تليفونكم لما في نيوتن. بحطوا الساتellite على الأوربيت تبعه following Newton laws. Engineering, construction, Newton laws. You measure the weight by Newton, and mass is a force. Transportation, sports and human movement, everything. Newton theory can explain everything around us, from the motion of planets to building a building. But there is only one thing that Newton theory could not explain. It could not explain this. Why 2 bodies with different masses fall at the same rate in point? They reach at the same time. So Newton himself, he could not explain. In Newton theory, to go more in depth in this thinking, don't worry, ما في formulate. There are 2 definitions of masses in the Newton theory. There is the inertial mass and there is the gravitational mass. Inertial mass is how resistant a body is to being accelerated. يعني هلا إذا عم تدفش فيات بونتو على الطريق غير ما بتدفش 6 wheel. And this is not related to its weight. Even in space, the mass resists acceleration. If you push a planet, you cannot push it away in space. If you want to push a small rocket, a small piece, you can push it away. This has nothing to do with gravity. But there is also the gravitational mass that tell us the more massive the object, the more it is attracted by gravity towards the center of gravity. So this is the first law, this is the second law of Newton, and this is the gravitational law. F equals ma, كيف تتذكروها الفورميل؟ A equal mg. كيف نحول من mass لفوق. So A is the acceleration, m is the mass measured with this principle. And there's another way, the definition of mass in the gravitational field. The force of gravity is proportional to the mass of 2 objects. So imagine the sun has a mass m, and the earth has a mass small m. The force of gravity between the sun and the earth is the product of the masses of the sun and the earth divided by the square distance. And for some strange reason that Newton could not explain, why these 2 masses cancel out. Why the inertial mass is always equal to the gravitational mass. A priori, these are 2 definitions of masses, and a priori there is no reason why these masses should be equal. This is 2 completely different definitions of masses. بعلمونا بالمدرسة mass quantité de matière بقلب. This has nothing to do with reality. Einstein came 300 years later, and he was thinking about Newton. Why Newton theory cannot explain why two objects fall at the same rate. And he imagined an experiment in which, imagine you are in a box, a closed box, and the box starts accelerating up in space. You are away from any planet, there is no gravity. ما في pesanteur حتكون. You will feel your weight pressed against the floor of the lift because the lift is accelerating. So you will feel your weight. So this is the acceleration. هلا نحن on the surface of the earth we accelerate at 9.8 meters per second square. يعني إذا بنترك object falling, every second the speed will gain 9.8 meters per second. Okay? But there's another acceleration that is the acceleration due to gravity. So if you take this lift and put it on the surface of a planet, you will feel your weight. And the main idea of Einstein, his best beautiful idea that he told himself, that there is no way you can tell the acceleration due to gravity from the acceleration due to movement. So you are in this lift, the lift is moving, you feel your weight, or the lift is put on the surface of a planet, you also feel your weight. And if the lift is closed, you cannot tell the difference, and there is no experiment you can do that can tell you if you are accelerated in a gravitational field or due to movement. And he predicted, with an amazing, brilliant thought, the bending of light. So imagine if you are in the same box, in the same lift, you shine a beam of light. The beam of light will go from here to there, it will reach the same height on the wall. But if the lift moves, accelerates up, and you are inside the cabin, the beam of light will go to the other side of the lift. You will see that the light has bent when you are in the lift. Because of the equivalence principle, because there is no experiment you can do that can tell you the difference from acceleration due to movement and acceleration due to gravity, if you put this lift on the surface of a planet or a very heavy object, light will bend by itself. Amazing thought, unbelievable, without any experiment, just in his head. And we observe the bending of light every day. People observe this every day in astronomy. Light bends next to a very heavy object, next to a black hole or next to a cluster of galaxies. And since gravity acts on light and light has no mass, right, then gravity cannot be a force. And he derived a notion of gravity that is not a force. So we'll go back to the insect living on the surface of the sphere. Imagine two insects on point A and B moving. They start parallel at the equator, but they meet at the pole. These are two-dimensional creatures. What mysterious force draws A to B? Nothing. There is no force. This is just geometry. So he thought of gravity as geometry of space, and this affected not only by mass, but by energy. Remember, E equals mc squared. Energy is equivalent to mass. Please ما حدا يخاف بس على السريع لكم. These are the equations of Einstein that describe the motion of the universe. So when he wrote his equations, A is the size of the universe. And A dot هذا term is the derivative of A. شو derivative تبع position vector with respect to time؟ حدا بيتذكر؟ Vitesse is the velocity. And this is the second derivative, it's the acceleration. So when he wrote his equations, حتلاقوا انه هيدي الاكسلريشن منا zero, because rho is the density in the universe. It cannot be equal to zero. But by the time Einstein wrote his equations, people told him the universe was static. It was not expanding. So for the universe to be static, these two should be equal to zero. Because the universe, astronomers told them, Einstein didn't know. Astronomers told him the universe is static. It's not moving. So he had to introduce a constant of integration. He called it lambda. And this is him drawing lambda on the board with the theta. To make sure that these are zero. So you can say any value to lambda, and this value will become zero. But later, when Hubble told him the universe was expanding, there was no need for lambda. He removed it from his equations. And then he referred to it as the biggest mistake of his life. Einstein said, wow, I could have predicted the expansion of the universe and could have been very famous. He didn't. So, in full formula, imagine this. If the universe is expanding and has mass inside it, and mass has gravity, it has to decelerate. It is accelerating, and it should be decelerating. So when you throw an apple in air, the apple will go up, right? It will reach a point, it will stop, and it will fall back. هذا البرنسيب تبع kinetic energy and potential energy. So you give it kinetic energy, you give it a velocity, 1/2 mv squared, it goes up. The kinetic energy reduces at the top, and it gains potential energy, and it falls back. Now you can throw the apple higher as much as you high, as long as you give it a velocity that is high enough. But there is one velocity, it's called the escape velocity. You can throw the apple, and the apple will escape the gravitational pull of Earth. This is how they send rockets to space. This will fly to space, but it will keep decelerating. It will go to infinity, but at a never decreasing speed. So the universe has mass inside, and if the universe is expanding, it should reach a point, either fall back on itself, collapse back on itself in something called the Big Crunch, not the Big Bang, or keep expanding at a never decreasing rate for the future, for infinity. So this is the universe. Imagine the universe starts expanding. The universe has matter in it. Matter exerts gravity. Gravity pulls things. It slows down the expansion. The universe has, and it falls back on itself as in something called the Big Crunch. Or it can keep expanding forever. So if you plot so when I say the fate of the universe, what I mean is the size of the universe. So on the y-axis you have the size of the universe, and on the x-axis this is an axis of time. Okay. So if the universe starts small, it goes larger in time. If it's on this track, it will go large, then it will collapse back on itself. Or the universe has the escape velocity that the apple has, and it will escape to infinity. It starts accelerating at a never decreasing rate. اللي بيصير يوسع النيفير بس asymptote بيصير أبطأ وأبطأ 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 للإنفيني. And we are here. This is the present time. And مين في اللي what is the slope of this line? The slope of this line is the Hubble constant. This is the rate. This is the derivative of this function. Okay? So we sit here and we look, and astronomers wanted to know if the universe is expanding, what is the fate of the universe? The universe will collapse back on itself. So how do we do this? We sit here. We cannot look in the future because it's the future. What we can do in astronomy, as I told you from the beginning, we can look distant in the universe, and by looking distant, we look in the past. So we look in the past, we sit here, we look in the past, and we should find objects for which we can measure time when the light was emitted, and the size of the universe when the light was emitted. And we could see where they fall, if on this track or on this track. Clear? So how do we measure time? By measuring time, we need to measure distance. So how do we measure distance? It's very difficult to measure distance in astronomy because you see things in the sky, you don't know how deep they are. You can measure angles only. Unless there is something called the standard candle. So if you have a source of light for which you know the amount of light, and now lamp it meet what, I can know how distant is the lamp from me, right? Because I can measure the flux I receive, and this flux is proportional to the square of the radius. And هلا أنا عم بحكي اللي بأول row عم يسمعوني. Those who are 2 times away will hear me 4 times less. Those who are 5 times away will hear me 25 times less. Because this energy is transformed to a sphere, and the sphere has the area of 4 pi r squared. This is the same with heat. وقت تحطوا ايدكم حد الشمينيه وقت تبعتوها وين بتحسوا انه الحراره خفت؟ لانه it's the square of the distance. Okay? So اذا انا بعيد عن الشمينيه 5 مرات لو بحس 25 مره قلب الحراره من اللي قريب مره واحده على الشمينيه. So this, if I know the source of light, I can tell the distance from this law. So what we do, we look distant in the far universe, and when we look distant, if objects are faint, they are far, and then we look back in time. We can measure time. The objects who are bright, they are nearby, and it is the present time. objects who are dim, they are distant, and we look in the past. So we measure time because time is distance divided by velocity, right? Velocity is the speed of light, it's constant. We measure time by measuring distance. So this is how we measure time or distances in astronomy. The second thing, how we measure the scale of the universe. So the universe, when light was emitted, this is the wavelength of light that I explained in the beginning. Imagine a wave of light on this rubber band, and somebody comes and stretches the rubber band. Then the wave of light has been stretched. So this is what I explained to you before, the Doppler effect. It's not actually Doppler. It's because the light has traveled in the universe and the space has expanded meanwhile, so the wavelength has expanded. And you can measure the difference between this, and this is called the redshift. I told you about the redshift before. And from the redshift, we can measure the size of the universe when the light was emitted. So if you look at the redshift of 1, you have here 1/2, and the universe was half its current size. If z is equal to 9 plus 1, 10, 1/10, the universe was 1/10 of its current size. So A is the scale of the universe, and Z is the redshift. So to recap, we need to find objects for which we can measure the redshift, and the redshift would tell us how much the universe has expanded. So we have the distance on this axis, and the luminosity, which will tell us the time, we have this on this axis. Okay? And the universe gave us such objects. 3 objects in the universe, we know how bright they are, and they are called type 1a supernovae. These are exploding stars. They explode very bright. They are very rare events, 1 per galaxy per 250 years. Look at their rare. But the universe is so big and so old that rare events happen all the time. They shine like 10 billion suns. So if you take 10 billion of our suns, these things reach the luminosity of 10 billion suns in 20 days. Look at the supernova here. This is the light of hundreds of billions of stars, and this is the light of 1 supernova. And there's a way we can tell their luminosity. What are these objects? They are small stars of carbon. So our sun in the future, when it dies, it will become a white dwarf, une naine blanche. So it's a ball of gas of carbon and hydrogen that is 1 million times denser than water. The density is 1 billion kilograms per cubic meter. And for some reason, these things explode by throwing matter from a companion star. So this is a cartoon analogy. So this is the white dwarf, the red giant, and it pulls matter. The density increases in the white dwarf, the density and the temperature, and it runs a thermonuclear reaction, a detonation, and they blow with a huge amount of light. And you can see these things. Look, this is supernova growing bright. 20 days it reaches peak brightness, then it goes back. And there's a way we can know how much light these things emitted. And this is our standard candle. This is the 100-watt lamps that we need to measure distances in the universe. This is another one. In 1988, 2 groups of astronomers wanted to measure the accelerating rate of the universe using type 1a supernovae. This is the IZ supernova team and the Supernova Cosmology Project. This guy was between these 2 groups. They got the Nobel Prize in 2011 for discovering the accelerating universe and dark energy. So they were working separately. These things are very difficult to see in the sky. This is other than the images I showed you. So this is a real image from the telescope. This is the galaxy before the supernova. This is the galaxy after the supernova. Can you tell the difference by eye? So this is this. So they take the CCD and they subtract each pixel minus each pixel to see the difference. And this is the supernova. So these are very hard to detect, and they are really far in the universe, very distant in the universe. This is another one. Look, it's just a pixel of light. Okay, and so what they do? So I'll show you technique. What they do. So this is, you remember this famous plot. The universe can. This is the axis of time, and this is the axis of the size of the universe. The universe can grow old and then collapse on itself, or it will grow for infinity. What they take, they measure the redshift, but they put the redshift on the x-axis, not the y-axis, and they put the brightness on the y-axis, which is a unit of time. And they take the center of the plot here now. So this is the present time. It starts from here. This part here that is in the future, it is not represented on this plot. So they should find supernovae, they measure the redshift of the supernova, and they measure the luminosity of the supernova, and they can plot the history of expansion of the universe. لأعطيكم analogy, if you were a police officer دركي أنت وعندك سيارة جاية من طرابلس على بيروت، ما بتعرف قد ايه سرعة السيارة، بس عندك صورة وعندك الصورة وين متاخدة؟ وحدة اتاخدت بالباترون وحدة بالجبال، فيك تعرف إذا هالسيارة كانت عم accelerating ولا decelerating؟ Obviously فيك. And this is exactly the method that they use. So this is the real data. This is the data that got Nobel Prize in 1988. So the black line, so they took this plot and so this is the residual. يعني هيدي minus هيدي ليبينوا لأن هيدي logarithmic scale. So the blue line is the universe that will collapse back on itself. This is the heavy universe that is very massive, has a lot of matter. And the black universe is an empty universe, it's a universe that expands without matter. It does not accelerate, neither decelerate. And the data all showed they are above this black line. You can see here. So there are maybe 20 or 25 points above this black line, even with the margin of error. So it's not a hazard. يعني ما فيك it's like tossing a coin 20 times and getting heads كل مرة. كانك ترى راسها بتلعب 20 مرة بيجيك ترى راسك. Probability تطلع 1/2 to the power 20. بيطلع 1 in a million. If you take 30 points, it's 1 in a billion. Now there are hundreds of points beyond. This is the data from 1988. It's old. Now they have more data to see that the universe is expanding. It means it was slower. It's accelerating. It means it was slower in the past. So the data is not here. It is not here. It turned out that it was here. Unbelievable. And this means, what does this mean? It means that I threw the apple, and instead of for the apple to decelerate, to slow down, it started pushing, like something is pushing on the apple up. It's something like anti-gravity pushing on the universe to accelerate its expansion. And this is the track on which the universe, if we extrapolate, is. So the universe is not coasting, it's not closed. It will not extend forever at an ever decelerating rate. It is accelerating. Okay? So people call this dark energy. So people have no idea what it is. بس بدل ما يقولوا للعالم ما بنعرف شو بيقولوا we discovered dark energy. And they got the Nobel Prize in 2011. Okay? So the data extends to very high number of supernovae. This is a collapsing universe. Look where the data is. So this thing is real. And people don't understand what it is. So they thought about it. And they got back to Einstein equation. Said, wait, Einstein had lambda in his equation. And he removed it when we told him the universe was expanding. But maybe we need lambda to explain the accelerating expansion of the universe. So تطلع بهذه الإكواسيون, you can see if A gets bigger, the size of the universe gets bigger, this term gets smaller, right? But these terms make sure that A increases with time, the velocity increases. And this makes sure that the curvature of the slope, the second derivative, is positive. So it is curving up. And people think now that, or some people think that dark energy is nothing but the cosmological constant lambda that Einstein included in his equations for completely other reasons. Then he removed them. Then they put it back to that. So what does this mean for the fate of the universe? Just one more thing I will tell you. I told you about the supernovae, but there are other experiments that tell the universe is expanding. This is the cosmic microwave background. This is the oldest picture of the universe. It is 380,000 years after the Big Bang. So what happened? The universe was so hot, and when the temperature is very high, light cannot travel. It bounces back on free electrons. And مثل السيرفس of the sun, إذا بتطلعوا على السيرفاس تبع الشمس, you cannot see beyond it. ما في حائط بيتون, because you cannot see beyond because it's very hot and light is trapped inside until it reaches a surface where it's cold enough where the light can escape. So the universe was very hot. By expanding, it became cold enough, and this allowed the light to escape. It's like the universe took a selfie of itself. Okay? And when he was very young, 380,000 years after the Big Bang. And what you see here are density fluctuations. By the way, if you don't know what this is a picture of the whole sky. هذه بروجيكسيون كيف بيعملوا بالخرايط they project هيك وهيك. So this is the whole sky 360 degrees هيك و 360 degrees هيك but it is projected. So the density fluctuations are in the order of 1 in 100,000 but they can be measured. And these are sound waves traveling in the plasma for 380,000 years, and people can know the distance of these density fluctuations, and they can compare them to what is the universe doing now. And they have, instead of a standard candle, they have a standard ruler. So they can know how the universe evolved, if it's accelerating or decelerating, so they can measure the luminosity and the redshift from a completely different method that gives the same result as the supernovae. Another thing, from the simulations with dark energy on the large structures of the universe, so when you make a model, theoretic model, you put all the physics that you understand, and you make it develop, and you have a universe that looks exactly like the universe that we observe in the telescope. So what does this mean for us? This is the famous sharp pie of the universe. So the universe, the composition of the universe, is made from things that push on the universe to make it accelerate faster and faster. This is dark energy, okay? And the other part is made from things that pull on the universe, that exert gravity. This is the matter that we know, the bionic matter, the atoms. So this is all the atoms that we know, اللي معمولة من atom, okay? It makes only 4.6 or let's say 5% of the constituents of the universe. The other part of matter I didn't tell you about because it's a long story. There's a part of matter that exerts gravity but does not interact with light. And this matter is called dark matter. If people know that dark matter exists, I will tell you how. But this is the famous chart pie of the universe. So the density of dark energy is 10 to the minus 7 kilograms per cubic meter, or 10 to the minus 10 joules per cubic meter. It's very, very, very small. So people know that dark matter exists because of the rotation of galaxy. I will not take you through this. So what does this mean for the fate of the universe? It's a battle between dark matter that pulls gravity, that pulls the universe back, and with dark energy that pushes on the universe. So what does this mean? If this dark energy is the cosmological constant of Einstein, then as the universe evolves, it will remain constant, right? Because it's constant. But the density of matter will drop with time. Because the universe is expanding, there is more space, but the same amount of matter in a bigger volume, so the density will drop. And the universe will be dominated by dark energy. This means the universe will continue expanding at another decelerating rate, pushing galaxies beyond our cosmic horizon, until one day we are left alone in a dark place. And if zero galaxies drifting away from us faster than the speed of light, and astronomers in the future will look far using their sophisticated telescopes, and they will not see any galaxy, because galaxies have gone beyond our visible horizon. And we will remain in our galaxy until all the stars have died, all the gas have been used, and it will become total darkness. The second thing is, what if dark energy decreases with time? So this can lead to a big crunch, so gravity can take over with time. Now this is a simulation, by the way. This is a very recent simulation. If you saw in the news, it was announced 3 weeks back, the dark energy. These people will get the Nobel Prize maybe after 20 years. So every point you see in this picture is a galaxy. Every dot, every pixel is a galaxy. So we are here at the center. This part we cannot see because it's obstructed by our galaxy. We look up and down, and they have hints that dark energy has decreased over the 7 billion years, like 10%. But we don't know what the future may be. So if dark energy is not constant, and if it does decrease, if it will increase with time, it means this thing will get created more quickly than the creation of space. Now I told you the universe is expanding, galaxies are going away from each other, but the galaxy itself is not expanding because it's held by gravity. And dark energy on a small scale is very small. Me and you are not expanding because we are held together by our molecular bonds. Our sun is not expanding because it's held together by gravity. The solar system is not expanding. But if this dark energy will become denser, so you put more of it per cubic meter, then this dark energy will take over and every bit of space will start expanding. It means the galaxies will expand, will fly apart, the stars will fly apart, the planets will fly apart, our molecules in our body will start flying apart, the atoms themselves will fly apart, the constituents part of the atoms will fly apart, and this catastrophe is known as the Big Rip. So the universe will, dark energy will take over and the universe will be ripped apart in every corner at every scale of the universe. But who knows? Not only the universe is stranger than we imagine, it is stranger than we can imagine. Thank you very much. Can you start, please?